Welcome to the HT8 MCU basic tutorial on LCD drivers. This course will guide you through the LCD driver features of HT8 MCUs. We will cover the following 4 topics: LCD introduction, LCD operating principle, LCD driver structure, and LCD registers. LCD introduction. What is an LCD? An LCD, or liquid crystal display, is a display component that utilizes the optical properties and physical structure of liquid crystal molecules to visualize various status information. Liquid crystal is a voltage-integrating material, meaning its twist angle depends solely on the RMS voltage applied across the electrodes, and is independent of the charging waveform. Now, let's look at some key LCD characteristics. The RMS voltage threshold that distinguishes between the on and off states of an LCD is called the threshold voltage. When the applied RMS voltage exceeds the threshold voltage, the LCD pixel turns on. Conversely, it remains off when the voltage is below the threshold voltage. Next, let's look at the types of LCDs. First, the segment LCD. A segment LCD is a fixed display that shows or hides predefined segments at specific locations. It can only display simple characters, digits, or symbols. Segment LCDs are widely used in automotive instrument panels, beauty devices, small appliances, watches, electronic scales, calculators, and similar products. On the other hand, the dot matrix LCD is composed of numerous pixels. In a dot matrix LCD, pixels are arranged in a regular grid of rows and columns. Each pixel corresponds to a small region within the liquid crystal layer, along with its associated components such as backlighting and color filters. Each pixel is independently controlled, enabling the display of fine, high-resolution images. Dot matrix LCDs are widely used in smartphones, tablets, televisions, and similar devices. A normally white LCD, abbreviated as NW-LCD, appears bright when no voltage is applied, because the liquid crystal allows light to pass through. When voltage is applied, the liquid crystal blocks light, resulting in a dark appearance. As shown on the right, a normally white LCD has a white background with black characters or symbols. Conversely, a normally black LCD, abbreviated as NB-LCD, appears dark when no voltage is applied, as the liquid crystal blocks light. When voltage is applied, the liquid crystal aligns to allow light to pass, producing a bright display. As shown on the right, a normally black LCD has a black background with white characters or symbols. We will now understand the key parameters of an LCD driver. The first parameter is the driving voltage. Liquid crystal molecules must be driven by an AC voltage. Applying a DC voltage for an extended period will cause irreversible electrochemical degradation. This leads to image blurring and a shortened lifespan. The second parameter is the frame frequency. The frequency of the AC driving signal is determined by the LCD panel's size and design, typically ranging from 60 to 100 Hz. If the frequency is too high, power consumption increases. If it's too low, visible flicker may occur. The third parameter is the duty, also known as the duty number or COM number. In the time division dynamic scanning method used by STN and TN LCDs, the duty, representing the fraction of time each COM line is selected during one full frame, is fixed and equals 1 divided by the total number of COM lines. As shown on the right, in a 1/4 duty configuration, each COM is selected for 1/4 of the frame 0 period. The fourth parameter is the bias. The drive waveforms for LCD seg and COM lines are analog signals. The ratio of each voltage level to the maximum LCD output voltage is called the bias. Bias is defined as the lowest output voltage level divided by the highest voltage level. Common configurations include 1/2, 1/3, and 1/4 bias. There is a critical relationship between the COM number and the bias. As the number of COM lines increases, the scanning time available per COM decreases. To maintain the same display contrast, the ratio of RMS voltages between the on-state and off-state must increase within the screen's tolerable voltage range. This requires a larger voltage difference between selected and non-selected states, meaning a higher bias is needed. Note that a higher bias increases the driver's power consumption. There is an empirical formula between the number of COM lines and the bias is. Holtec's LCD type MCUs provide a variety of LCD drive methods, as listed below. Taking the model HT66F3195 as an example, it uses the SCOM plus SSEG drive method. The LCD drive pins, including SCOM0 to SCOM21 and SSEG0 to SSEG25, are shared with the general-purpose I/O ports. The drive signals for the LCD COM and SEG lines are generated by the application program. For more detailed information, please refer to the application notes available on the Holtec official website. LCD operating principle. Let's look at how to illuminate an LCD pixel. Each pixel is controlled by the voltage difference between one COM pin and one SEG. A pixel turns on when this voltage difference reaches the full VDD level. Let's take a practical example. Suppose we have the following pin configuration to control the segments of a digital display. For instance, to illuminate segment A, the voltage difference between COM3 and SEG1 must reach VDD. Now, let's see how to display the digit 5 along with the decimal point on a segment LCD. The segments that need to be lit are A, C, D, F, G, and DP. Their corresponding control pins are listed in the table. The figure shows the LCD drive waveform configuration for 1/4 duty and 1/3 bias. With 4 COM lines, the duty is 1/4, meaning each COM line is selected for a quarter of the full scan cycle. The drive waveform uses 3 voltage levels. VDD as the highest, with 2/3 and 1/3 of VDD as intermediate levels. Thus, the bias ratio is 1/3. One complete LCD waveform cycle consists of 2 frames, frame 0 and frame 1. During the first time period of frame 0, COM 0 is selected and outputs VDD, while SEG 0 and SEG 1 output VSS. The voltage difference between COM 0 and both SEG 0 and SEG 1 is therefore the VDD level. So the corresponding segments D and DP are illuminated. During the second time period of frame 0, COM 1 is selected and outputs VDD. SEG 0 outputs 2/3 VDD, and SEG 1 outputs VSS. The voltage difference between COM 1 and SEG 0 is only 1/3 VDD, so the corresponding segment E remains unlit. The voltage difference between COM 1 and SEG 1 is VDD, illuminating the corresponding segment C. During the third time period of frame 0, COM 2 is selected and outputs VDD. The voltage difference between COM 2 and SEG 0 is VDD, so the corresponding segment G is illuminated. The voltage difference between COM 2 and SEG 1 is 1/3 VDD, so the corresponding segment B remains unlit. During the fourth time period of frame 0, COM 3 is selected and outputs VDD. The voltage difference between COM 3 and SEG 0 is VDD, so the corresponding segment F is illuminated. Simultaneously, the voltage difference between COM 3 and SEG 1 is also VDD, which illuminates the corresponding segment A. Now let's look at frame 1. Essentially, frame 1 is the inverted output of frame 0. Why we say that? Let's look at the first time period of frame 1. COM 0 is selected, But unlike in frame 0, it now outputs VSS, while Seg0 and Seg1 output VDD. The voltage difference between COM0 and both Seg0 and Seg1 is negative VDD, which is exactly the opposite of frame 0. Despite this polarity reversal, the segments D and DP are still illuminated. The same logic applies to all other segments. This method constitutes the AC driving of LCDs. The key is that within one complete waveform cycle, each pixel is driven once in the forward direction and once in the reverse direction. This is crucial to ensure the long-term reliability and lifespan of the LCD pixels. LCD driver structure. Taking the HT66F3195 as an example, its LCD driver structure, as shown in the figure, can be divided into four main parts. The first part is the bias resistor selection. Choosing different bias resistors results in different bias currents. A higher current generally provides greater display contrast but increases power consumption. Conversely, a lower current reduces both contrast and power consumption. The second part is the power. It is controlled by the LCD EN bit, which is used to enable or disable the entire LCD function. The third part is the output frame selection. It is controlled by the FRAME bit, which selects whether to output frame 0 or frame 1 waveform. The fourth part is the output terminals. The specific I/O pins used for LCD driving are selected through a combination of the LCD EN bit in the SLCDC0 register and the related pin function selection bits. Please note that for LCD drive operation, the associated I/O port control registers do not need to be set to output mode. LCD registers. The register SLCDC0 is the control register for the LCD module. The FRAME bit selects the output frame, either frame 0 or frame 1, for the SCOM and SSEG pins. The ISEL1 and ISEL0 bits select the appropriate bias resistor for R-type LCD. The LCD EN bit is the master control bit that enables or disables the entire LCD module. The registers SLCDS0 through SLCDS2 are the pin function selection registers. To illustrate, the COMSEGS21 bit in the SLCDS2 register is used to select whether the corresponding pin functions as SCOM21 or SSEG21. A complete listing of all registers and their specific functions can be found in the HT66F3195 datasheet, as covering each one in detail is beyond the scope of this video. Course summary. This concludes our course on LCD drivers. We have covered what an LCD is, its operating principle, driver structure, and associated registers, giving you a comprehensive introduction to how they work. Holtec provides a professional service team to support your development design and offer after-sales service. For more detailed product information and consultation, please feel free to contact our business departments.